We're happy that we were able to drag Nigel Goldenfeld all the way from lovely Urbana, Illinois, so that he could enjoy the weather here. And he's going to talk to us about, he said, really, you guys want to, what do I do that's to do with topology? He said, it's all topology. So, here you go. Thank you.
Okay, so Randy, thanks for inviting me. It's been a pleasure to be here today. So I'm going to talk about pattern universality and computational algorithms. So at least the first talk today, I understood that one. I had no idea about the second talk. Hopefully, this third talk will be understandable to you guys. I'm a physicist. I'm not a mathematician. So it's not false modesty when I say I don't know anything about topology. I really don't. But anyway, there is some interesting topology stuff that's in this talk. So maybe you'll find it interesting. So I'm going to talk about work that is a mixture of old work and new work. And so let me switch this on. So let me tell you what I'm going to try to explain to you. So I'm going to try to explain to you about minimal models and universality. So in other words, how one can try to describe physical phenomena in the most parsimonious way, and how to do that, and what can we reasonably expect as the sorts of questions that we can ask and answers that we can get. So I'm going to start telling you about that, and then I'm going to talk about how we do modeling, and I'm going to try to sell you on an idea that the best way to do modeling is by forgetting about calculus and for looking at dynamical systems as a kind of cellular, spatially extended system. So I'll show you how that works. Now, people, of course, are very familiar with that sort of idea. And for example, you can look at, say, cellular automata and look at the patterns that cellular automata make, and you can say, well, these patterns look like snowflakes or scallops on shells and so on, and you can make them make pretty patterns. And but I think that that kind of statement doesn't quite go far enough. And I want to show you that, in fact, one can really make quantitative statements about patterns and their space-time behavior, and even make predictions that can be tested experimentally and have been tested experimentally. So that's up to here. And then I'm going to talk at the end of the talk, if I have time, about a different way of modeling systems that can show topological features, which are materials systems, atoms that like to be next to each other to form crystalline or polycrystalline materials. And I'm going to show you how to do multiscale simulation and even do molecular dynamics and even simulate foams, although I won't be able to show you that in the talk, but using a very nice sort of macroscopic approach. So everything I'm going to talk about is basically informed by a perspective on the way to do physics that comes from phase transitions in the renormalization group. And so I'm going to explain that as well, because I understand that that also is something that's close to the interests of people involved in this workshop. So let's start off in a very simple way by just looking at the different ways that we model reality. So here is a picture of a polymer as viewed by, let's say, a chemist. So you've got a bunch of atoms, and he made some ball and spring model of some kind of a polymer like that. So that's one picture, an atomistic picture of a polymer. This is how my colleagues who work on computational biology think about polymer molecules. So this here is some computer simulation of a biological molecule, and basically what you have here are some atomistic complexes. You have some sheets of beta sheets, you have some alpha helices, and you can describe the system by some kind of elasticity theory for some of these parts, treat them as bending beams, treat them as springs in other parts, treat them as atoms in other parts. So that's a sort of computational biologist's view of the world. So this is a theoretical physicist's view of the world. Of the world of polymers. So basically it just says that polymers are long stringy objects, and the question that we want to understand is what properties of polymeric matter can be understood just by knowing that they're made out of stringy stuff as opposed to round blobby stuff. So the kind of universal question you want to ask is, does anything non-trivial and really non-trivial follow from just the fact that you know it's made out of this? Well, the answer is actually a lot. I'm going to tell you about some of the things here. But for example, we understand a lot about the statistics, we learn a lot about the structures, we can even learn about the transport of polymeric matter just from knowing it's made out of long stringy stuff. So these different descriptions are all valid. No one is better than the other. They're just better at answering different kinds of questions. So the chemist is interested in chemical bonding and reaction theory. The computational biophysicist is interested in looking at elasticity, they're interested in looking at large-scale motions, folding, and so on. And the physicist might be interested in understanding, say, the thermodynamics of polymer mixtures, or light scattering from polymers in solution, or the rheology of polymer melts. So all of these different descriptions are suited for a different type of question. Let me give you an example of how that thinking can work and how it can fail. So let's ask the very simplest question that one might think about, which is, how big is a polymer? So what do you mean by how big is a polymer? Well, you have to tell me how many monomers there are inside the polymer, how many bits, identical units, are strung together. So that number is n, and each monomer is of length little l. So the total arc length of the polymer, if all the monomers were laid out end to end, is just capital L. Now, of course, polymers don't lie out end to end. They, in solution, they're floating around in some kind of structure like this. And so what we really want to know is how big it is in terms of its radius of gyration, how big a space it occupies. That's the variable I've called r. So here's the way that a theoretical chemist might go about answering that question. The chemist might say, well, what you do is you model the bond angles from the different atoms that are in there. You model the energy barriers to the rotational states as the atoms rotate about some bond. You look at the interactions with the solvent molecules, and then you stick this thing into a big computer. You sample over long times or many configurations, and at the end of the day, you predict what R is in angstroms. And that's the answer. The physicist doesn't say that. The physicist says, oh, well, this is simple. This polymer is just a random walk of n steps, each of length L. So that means that it's just a random walk. We can use Einstein's argument, and we get R squared goes like n, or R goes like n to the 1/2. And the physicist is very happy with themselves. But first of all, there's a couple of problems here. So first of all, the main problem is that this answer is wrong. It's completely wrong. Why is it wrong? Well, atoms can't occupy 2 points in space. So there's an effect called excluded volume, which says that the polymer string is not just a string. It mustn't intersect. It mustn't self-intersect. Well, what that means is then that the polymer is going to be slightly bigger than it would be if it was just a random walk. And how much bigger? Well, we now know that the answer is that instead of R scaling like L to the 1/2, R scales like L to the 0.588, etc., etc. Some transcendental number like that, and that's an asymptotic statement as L goes to infinity. And we also know that this scaling is something that is universal. It's independent of the chemical structure. It doesn't matter whether you're looking at polyethylene or polydimethyl methacrylate or anything like this, DNA. This is always going to be true as long as you're in this asymptotic regime. So the other thing is about this answer, the physicist's answer, is it's completely worthless. It doesn't predict R in angstroms. Now, it's not quite worthless, because if the chemist then says, well, actually, I told you that the length of the polymer chain was 100,000 repeat units. Actually, it's going to be 300,000 repeat units. How big is the chain now going to be? Well, so the chemist would have to go back, redo the entire calculation. But the physicist knows that if you tell me what the answer is for 100,000, all I've got to do is put that into this formula here. I know how it scales with the number of repeat units, and so I can predict the answer with no additional work. So this does have some value, but it's a different sort of question than looking at the size in angstroms. Now, there's other things that one can do. So here is a lovely example that is a plot of the pressure, the osmotic pressure of polymers in solution, as a function of the concentration of the polymers. So you just take polymers, you just stick them into water, and you measure how many you put in, and you measure the pressure, the osmotic pressure in the solution. So physicists and chemists know how to do this. And what you find is the following. The same kind of theory that predicted that L to the 0.588, etc. Exponent also predicts that if I take the data, plot it in a certain way that the theory predicts, in particular plotting C over some variable C star, which I'm not going to explain to you what that is. If you plot the data in that way, it says that all the data for all different polymers, whatever they may be, should all fall onto one universal curve. And moreover, you can calculate what that universal curve is with no adjustable parameters. And that calculation was done by Otto and Ono in 1982 and checked in experiment by Pierre Wiltzius the following year. And so this is, the point here is you've got data collapse. Everything is universal. There's no adjustable parameters. There's no material-specific parameters. So this is a very interesting, a very non-trivial kind of question that one can answer just by thinking about the spaghetti nature of polymers. Whatever kind of description you have of polymer molecules, however you microscopically understand them, they're forced by the stringy nature of them to obey these kind of laws on large scales. So this is an example of what we like to call a minimal model. A flexible random walk is a minimal model. A self-avoiding walk is a minimal model. They're good for answering certain questions, like the pressure, scaling of size, the number of monomers, but they're lousy at answering other kinds of questions, such as what is the size of a polymer coil in angstroms. Now, the method that physicists use to understand these sorts of problems comes from the theory of phase transitions and quantum field theory, and so we now understand the mathematics of this, or at least at the level of good enough for physicists level. We understand that very well, and we can explain the thermodynamics and the structures of critical points and so on and so forth. We can also understand dynamical systems phenomena in ordinary differential equations and partial differential equations and iterated maps, also using renormalization group methods. And if you want to learn about it, this is a plug for my textbook on that subject. But in particular, where I do try to separate the renormalization group ideas from the statistical physics mumbo-jumbo, which is of peripheral relevance to this technique. This technique has a lot broader significance than just statistical physics. So now I want to talk about patterns, and one of the things I want to make, one of the points I want to make, is that successful scientific predictions are always the results of minimal models. So up to now you might have said, well, I've shown you some examples of minimal models, and I've also pointed out how limited they can be. But now I want to point out that actually all scientific predictions are minimal models. And the reason for that is you simply can't include every detail in any model. So, for example, if you were, for example, a materials scientist or a chemist, and I asked you, well, when was the last time that you worried about the mass of the top quark in making a prediction or doing some experiment? Well, of course, the answer, it's a preposterous question. Of course, you never worry about the mass of the top quark if you're doing chemistry or material science or condensed matter physics. There's a separation of scales, and those details simply don't matter, and the fact that they don't matter has a non-trivial mathematical representation. So in physics, the reason it's so successful is that there's only a few details that are important. The questions we ask are really easy ones, and so we can make some progress. In chemistry, you usually need a lot more details at the atomic level, but there is still a separation of energy scales. Again, you don't have to worry about quarks, but you may have to worry about atomic and molecular interactions at many different scales, and that makes it hard. Then there's other problems, say economics, where we don't know if there's any simplification that can be made. Every detail seems to matter. Okay, so this is my last general slide of propaganda. So an example that I like to make is the BCS theory of superconductivity. So superconductivity is the phenomenon that happens in materials, some materials at low enough temperature, where they essentially conduct electricity with no resistance, and they also expel magnetic fields in a way that's very interesting. Now, the theory for this was developed at the University of Illinois by Bardeen, Cooper, and Schrieffer, and it's generally regarded as the most successful statistical mechanical theory of electrons and materials, and it has spectacular agreement with experiment. So I'm not going to, don't worry if you don't know what these quantities mean, it's not important. The theory predicts that there's a kind of energy gap in the spectrum of allowed excitations of the system, that energy gap delta divided by the critical temperature below which superconductivity happens, is predicted in this theory to be a fixed number, which they calculate, 3.53, and here is the data for that, and the slope here is exactly 3.53 for these materials to which the theory is supposed to apply. Similarly, if you look at how this energy gap varies as a function of temperature, again, that's predicted, the complete function is predicted, and it works very well with all the experimental data. So that seems to be great. However, if you ask, what is the critical temperature below which a material becomes a superconductor, we're completely embarrassed by that. We do not have a very good way to understand how to compute that. Now let's talk about patterns, and complex patterns, which is why we're here. So, so here is an example of a microstructure of a material. This is a microgram, and so here is some polycrystalline material. And if you blow up this part here, you see that the microstructure is made by this complex array of growing what are called dendrites. So this is the standard mode of solidification for all metals and many other materials too. And this is what you would see if you looked under a microscope. And the question we want to discuss is, can we model microstructure realistically using minimal models? So in other words, do we have to really understand everything about the physics and the chemistry and the atomic interactions and so on to be able to predict this kind of complex structure, or can we use minimal models to do that? So my answer is yes, we can use minimal models, and I'm going to explain to you how in this talk. Now, I have a kind of litmus test for the audiences that I give these sorts of talks to. So I'm pretty confident, very highly confident, that there are no materials scientists lurking in the room. Okay, well, I know you are, but you barely count these since you're postdoc here. So you're a lapsed material scientist. Okay, now, so if you're in the material science group, somebody will ask you, well, where is the scale bar on this picture? So if you look at an electron microgram, often people like to see a scale bar, so there'd be a little bar there, and it would say 1 micron or something like this. But nobody asked me that because I guess you don't care. But the other reason that you didn't ask is because you're also smart, and truth be told, material scientists don't ask this either, because everybody knows it doesn't really matter. You know that there's some scale here, which is basically microns or whatever it may be. It doesn't really matter what the scale is. What's important is the pattern. If I want to know how to predict this structure in microns or angstroms or whatever it might be, you just give me one length scale. If I can predict the pattern, given one length scale, I can predict everything else in the pattern. So it's not the important question. So I don't care about predicting for a particular metal or a particular alloy what the actual scale is of these dendrites. But what I do care about are the scaling laws and the fact that these things exist at all.
This is not the magnification of the picture.
No, it's not the precise magnification of it, no.
Not only because you make a circle to the square.
I squared the circle. It's a sketch. Anyway, okay. So I want to now sort of make contact with the first talk that you heard this afternoon, and tell you about an example of this, a very simple example, which is a materials microstructure. And the materials that we're going to talk about is what's called an AB alloy. So that's what a material scientist would describe it as. And what they plot up here is the temperature versus the concentration of one of the components of the alloy. Now, let's think about this in more interesting terms. It's getting near dinner time. So think of this as being your vinaigrette salad dressing. And you're sitting in a nice restaurant and you have some vinaigrette dressing. You're sitting there chatting to your friends, and then when you look down at your salad dressing, what you discover that the green lettuce is decorated by this horrible mass of blobby fat globules surrounded by this anemic-looking liquid, and you don't really want to eat it anymore. But it certainly wasn't served up that way. Now, what happened? So what happened is phase separation. It started off well mixed up in here, which is the one phase, and then at a lower temperature, it is thermodynamically favorable for the system to split into two coexisting phases. One which is oil-rich, and one which is vinegar-rich. And those two phases form spatial patterns. It doesn't just stay spatially uniform, but it forms spatial patterns, which I'll show you in just a minute. And physicists like to describe that by some kind of free energy function as a function of the concentration, which looks something like that. It has two minima, and those two minima correspond to these two coexisting phases. So what happens if you try to look at the time evolution of that kind of system? So I'm going to show you just a computer simulation, but this happens in real life too. So red is vinegar, blue is oil, let's say. And so what happens is as the time progresses down here, starting from this initial condition, the system forms these domains, and these domains coarsen with time, like this. Now, if I were to take this little portion of this picture, this is starting condition, and I were to photographically enlarge it, then I would get this picture here. And if I were to take this slice of this picture, and photographically enlarge that, I would get this one would give me this one. Now, my point is that if I look at any given time at this photographically enlarged set of conditions, I can't really tell statistically which one came from the time evolution and which one came from the photographic enlargement. So what that says is that there is some kind of dynamic scaling law in time here which is governing the evolution of the system. And this is shown here for this alloy system, where the only interfaces are domain walls between one phase, the orange phase, and the other phase, which is the blue phase. But the same thing happens if I were to do this process for a system which had a vector or a tensor order parameter, like a superfluid or a Heisenberg magnet or a superconductor or liquid crystals. And in that case, what you would see, and I'll show you this in a minute, are not the boundaries, the domain walls, but you'd see the topological defects. So let me tell you how we quantify this observation. And again, this was also something that you heard a little bit about from a slightly different perspective in the first talk. So of course, real material scientists don't do their experiments on French dressing. They use copper manganese alloys, which are much more expensive. And what they do is they scatter X-rays or neutrons or light off the system, depending on what the appropriate length scale is, and they measure what's called the structure factor as a function of wave number. So what this is, this measures the correlation function between a point here and a point here. It tells me how similar those 2 points are in terms of the local concentration. I'm not going to define this in detail, but that's roughly what it measures. And when this object has a peak, so this is in wave number space. So the space along here is called Q, and Q is inversely proportional to spatial distance. So this peak here in this data set here tells you what is the characteristic scale of the domains that you saw in this picture here. So these domains are statistically irregular, but they have a characteristic scale which is growing, and that's reflected in the fact that this peak here moves to smaller and smaller wave numbers, which means longer and longer length scales. And the intensity of the peak goes up. That reflects how precisely the ordering is working. Now, what happens is, if I were to take these data for different times, then I get these successions of curves here. And now if I do the following, I take this structure factor, multiply it by the wave number Q, where this peak occurs. Let's call that Q max, and plot on the horizontal axis the wave number scaled by Q max. Take that to the third power, plot it like this. All the data for the whole succession of times falls onto one universal curve. So that is how you measure this scale invariance that you could see with your eyes, the statistical scale invariance. That's how you measure it in an actual experiment. Now, how do we model that kind of phenomenon? So the usual approach would be to write down some sort of partial differential equation, and then you look at the partial differential equation and it's nonlinear, and it turns out you can't really solve it. So then you say, well, we're going to have to put it on a computer. So then you put it on a computer, so you discretize it, following the recipes that you get in the numerical analysis course. And then what you get then is a set of coupled maps. And then you go ahead and run those coupled maps in space and time, and you get the wrong answer. And the reason you get the wrong answer is because by discretizing the partial differential equation, you've introduced all kinds of secondary bifurcations and other instabilities into the numerical algorithm. So then you go and read a bit further ahead in the numerical analysis textbook, and you discover all sorts of tricks and clever methods that people came up with to try to get around these problems in order that they could then compute the solutions of nonlinear partial differential equations with fidelity. So what we're going to do is we're going to cut out the middleman, as it were. So instead of modeling modeling nature as a partial differential equation, which you then have to discretize, why don't we just start straight away at coupled maps? Take the same physics, exactly the same physics that goes into the differential equation, but now formulate it in terms of coupled maps and make sure that those coupled maps are injective. In other words, that irrespective of the spatial discretization, you always have the same fixed point structure. And that's what I'm going to show you now. So let me give you an example, which is the spinidal decomposition. I'm going to follow roughly what was done by Ono and Puri in 87 or 88, something like this. So the idea is you take the system, you divide it up into cells whose scale is of order the correlation length, and now let's look at what happens to the dynamics in each cell. Look at the concentration variable in each cell. Well, I showed you before the kind of energy curve that describes the dynamics. And the idea is basically that the system locally tries to minimize its energy, so it tries to find the minimum of this energy as a function of concentration. Now, you can see from this curve that I drew that what's going to happen is the following. If the concentration is somewhere up here, then as time proceeds, it's going to fall down this curve and eventually get to this minimum over here. If, on the other hand, it started over here, it would fall towards this minimum. If it started up here, it would fall to this one. And so I can draw a flow diagram. There's 3 fixed points, an unstable fixed point at this concentration, and 2 stable ones at the concentrations that correspond to the coexistence. Now, the point is, there's nothing special about this free energy curve. This free energy curve wasn't, sort of given to us by God or anything like that. We just made it up as a caricature of the system. It gives us the right phase diagram. So there's no point in trying to solve exactly the wrong differential equation. Why bother? Much better to solve any map that has the right fixed point structure that we have here, and then try to understand the dynamics of that. Now, we know that we're not going to get exactly the same small scale structure as you would get from this free energy curve, because we're not trying to do that. But we're interested in the large scale properties of the patterns. We're not quite interested in the concentration profile as you go from the red region to the blue region. Exactly how does it vary? Does it go as a hyperbolic tangent function? Does it go as some other function? Well, we don't really care about that. What we want to know is how does the system coarsen? What are the statistical properties of the domains? What governs the motions of topological defects and so on? And we don't care precisely about the detailed small-scale structure. So we're just going to choose maps that are computationally convenient, maps that are always injective, so they never bifurcate and give me trouble as I work with a grid spacing that is not infinitesimal. So the usual thing is you have to work with, take the continuum limit, work with an infinitesimal grid spacing in order to be sure that you've solved your PDE correctly. So what this method is going to do is going to give the large-scale structure without having to take that continuum limit. And what we're looking for is the universal properties of these maps. Now, once you've got the on-site dynamics, then all you've got to do is then couple the cells. Now, in the normal material science description, what you say is atoms of the different species can hop around on this crystal lattice. They can diffuse from site to site. All diffusion is the process of me looking around at my neighbors and seeing if they're bigger than me or smaller than me. If they're bigger than me, then I increase my concentration value. If they're lower than me, then I decrease my value. That's all diffusion does. It's an averaging process. So you can simply couple the cells by adding another rule into the evolution that looks at the local concentration around you and then makes the appropriate adjustment. And then lastly, if there's a global conservation law, then you implement that. So that ends up giving you a kind of pseudocode which looks something like this. So it's a discrete coupled map for the concentration at lattice site n at time t. And I'm not going to take any continuum limit, so dt and dx are order 1. And the the evolution of the system looks like this. I evolve by some map, which I've written down here, and then I subtract off anything that destroys the conservation law. Now, what is the map that I'm going to use? Well, any map that has the right fixed point structure. Here I've written down one example that was in one of our papers, and of course we never would compute with that because it would be very expensive. So you just simply implement the map as some kind of lookup table. And then this term here, this tells you that you have coupling between cells. So this says, look around you, that's the local average, see how much different that average is compared to the concentration at the sites that you're looking at, and then make an appropriate adjustment. And that averaging process, you don't have to do a Taylor series expansion of differential operators. All you simply do is say, let me make the most isotropic averaging that I can make on a lattice of my neighbors. So here, this averaging operator has these coefficients 1/6 and 1/12. In this example, those don't come from doing a Taylor series expansion of the Laplacian. What those come from is making an averaging and then looking at its Fourier transform in k-space and trying to make the isocontours as circular as possible. So you don't, again, get this from a Taylor series expansion, but this is something that in the continuum limit would reproduce the same physics as the actual differential equation that people normally write down. So this is an injective on-site map, and this algorithm is topologically stable in the sense that there are no numerical instabilities that can arise as artifacts. So let's see if it works. So the summary point is this algorithm models exactly the same thing as the partial differential equation. So what you would expect is that they should both be in the same universality class as the physical process. So does it work? So yes, so it works for the oil vinegar dressing. I'm not going to show you the results of that. Let me show you something that's a bit more interesting from your perspective, perhaps. So this is what happens when you look at a pneumatic film through cross polarizers. And so what happens here is you have liquid crystals that tend to line up, but if you put the light through cross polarizers, then what happens is you filter out different directions of the rotation of the electric field. And these kind of objects here are topological defects. They're monopoles in this particular system. And now what I'm showing you here is what happens when you run this experiment for different times. And what you see happening is that here you have many topological defects. This is after you've gone into the phase where this is stable. And after time proceeds, the topological defects move around, they annihilate, and there therefore become less and less of them. And so the average distance between the topological defects increases in time. So that's what you see in experiment. This here actually is a computer simulation. It's not an experiment. This is an experiment. So this is an experiment that was done by Nagaya et al. And the experiment, of course, has got many more defects than you could see in the computer simulation. And so here again you see frames from their video movie of the whole thing, showing you over 30 seconds or so the coarsening process as you look at the dynamics of this pneumatic liquid crystal film. Okay, so what I've shown you is that you can make pretty pictures that look like what you see in experiment, but we can actually also compute things in a quantitative way. So one thing that we did when we did these simulations was we looked at the topological defects, we found where they were, and then we measured their correlation function in space and time. And when you measure the correlation function, then you find that if I scale the distance and time in a certain way that I'm not going to go into, then you find that the data for the correlation function as a function of scale distance for different times all collapses onto one universal curve, and that's the squares shown here. This is exactly analogous to what I showed you with the copper manganese alloy, where I showed you the structure factor that the experimentalists measured and then how the data collapsed onto one curve by scaling with the peak wave number. This is exactly the same kind of scaling law, but in this case we're looking at the scaling of topological defects rather than the concentration order parameter. The x's and zeros, this cloud of data points going around these black squares, those are experimental data taken from that movie. And so what you can see from this is that the computer simulations, which is basically a 5-line computer code, predicted without any adjustable parameters, A, that there is data collapse, and B, what the scaling function is. And you can see that that works very well. So there's no adjustable parameters here. The solid line is a mean field theory calculation that was worked out by one of my former students, Feng Liu and Jean Mazenko, in an approximation that physicists use, which I'm not going to go into. And that also predicts this scaling curve very well. So it's not just that we can make pretty pictures by this kind of very simplistic modeling, but that we can also make quantitative parameter-free predictions. So take-home message from this is that even though these simulations are not grid converged, even though they do not come from discretizing a partial differential equation, this minimal model captures the most important parts of the data. Of course, if you want to know how big those, what the distance is between the topological defects in actual physical units, I can't tell you that. I don't want to tell you that. That's not the goal of this exercise. So,
with the data?
Yes.
So those data points are correlated, right? It's the same sample?
It's from this, yes, it's the same sample, yes. Okay, so what I've shown you is that all physical models rely on, all physical predictions rely on minimal models. Computational algorithms, even very simple 5-line computer codes, can model very simple space-time patterns, and they can make quantitative predictions of universal quantities which can be compared with experiment. So if you would try to simulate that pattern and understand it by conventional approach, it would have been a very tough thing to do because the patterns are so complex. I have many other examples of things like that in not just soft condensed matter, but in superfluids, even in looking at the way that landscapes evolve, in geomorphology of landscapes, looking at the interaction between fluid mechanics and crystal growth, and many other things like this. So this method is a very powerful method and is very suitable for looking at large-scale physical systems. So now I want to talk about multiscale modeling. So I want to talk about what one does when one tries to resolve patterns at both large scales and atomic scales simultaneously. So this part of the talk is going to be more technical, and I don't expect you to follow all the technical details. I'm just going to try to flash them to you and show you what's important and why, but not expecting you to understand everything I'm going to show you, but I'll be happy to answer questions afterwards. Okay, so basically what we're talking about is pattern formation in materials microstructure. So again, here's a sequence of photos that are not strictly speaking made from each other, but here's what an engineer would like to know. Here's what somebody who's got, say, a scanning tunneling microscope might be able to measure. And these different scales of structure are important for determining different aspects of the macroscopic properties of these materials. So people really, really do care about them. Now, people try to model these things, and the scales at which one models, both in length and in time, define for us different kinds of algorithms that people try to use and then try to patch together. So if you're looking at very small scales, quantum mechanics may be important. You may have to do some kind of what's known as a density functional theory. On a somewhat larger scale, you can do molecular dynamics, where what you do is you write down Newton's equations for every atom in the system, and then you try to solve those for everything. On larger scales, you might try to do Monte Carlo methods, where you try to simulate the statistical equilibrium of materials. And then on larger scales still, if you're, say, a Boeing engineer trying to design a material or try to make an airplane wing or a turbine blade or something like that, what you'll do is then you'll use continuum mechanics and try to write down partial differential equations in space and time that describe what's going on. So this traditional way of modeling is sequential and needs the separation of length and time scales. And all of these methods have their pros and cons, which I'm really not going to go into, but I'm going to tell you about a method that is very nice because it covers a much broader range, in principle, of this space-time phase diagram than most of the other methods. So it's called the phase field crystal method. That's what PFC stands for. RG stands for renormalization group, and AMR stands for adaptive mesh refinement. So what I'm going to show you is that there's a very nice minimal model that one can work out that works from atomic length scales up to macroscopic, is valid on a range of timescales up to the timescales of diffusion, automatically includes the discrete nature of atoms and captures crystallography, elasticity, plasticity, topological defects, doesn't require one to implement very complicated boundary conditions, makes no assumptions of scale separation, and is only a simple sixth-order nonlinear partial differential equation. Okay? So it's really a very powerful minimal model that really captures a lot of detail that are difficult.
What scales is that supposed to capture, though? It's not supposed to capture all the scales, is it?
It's going to capture scales down to the atomic scale.
Down to the atomic scale?
Yes, down to the atomic scale. So let me show you how, and it's going to do that in a way that's in the sense of minimal models. So I'm always going to be, you'll see as I proceed. So what is the goal of multiscale modeling? So think of it in this way. Let's suppose I have some field psi, which is defined on space, and I know how it evolves in time through some nonlinear operator, so I can go from an initial condition to a final condition. Let's suppose now that I know that my initial condition, of course, has got much more information than I actually need, so I can define some kind of coarse graining of that initial condition up to, and we'll make a new field which we'll call capital psi. Similarly, I can apply that same coarse graining operator to my final state to get psi of x and t, capital psi. And now the question is, what is the operator that connects capital psi at time 0 to capital psi at time t? Microscopically, it's this, whatever this nonlinear operator was, but what is it for this coarse grain description? So that's really the question that we're trying to understand.
So you're coarse graining at what scale here in this picture?
I'm going to make it more explicit for you now. Okay. So the second thing is that when you coarse grain, why do you do that? Well, the reason is you want to look at the representative behavior of many degrees of freedom. So let's suppose we look at this process here, a polycrystalline domain that is growing in some material. So you could say, let's simulate the behavior of every single atom that I'm showing you here. These black blobs are meant to be atoms. But that would be silly, because you know that the atoms inside this region here are all basically doing the same thing. They're just sitting there basically doing nothing. What's the point of wasting computational power on these atoms in here which are doing nothing? We can just replace them by some effective degree of freedom. Now, where is the effective degree of freedom going to be actually doing something non-trivial? Well, it's only going to be at the boundaries where I've drawn these red circles here. So the idea is that we can coarse grain in some dynamical way by trying to find some way to find a representative of all these degrees of freedom and then put all our computational power at these edges here where there are domain walls or topological defects and so on. So the basic idea is that we can make a systematic reduction of the number of degrees of freedom, but we want to do this not just in space, which is just a question of spatial filtering, but we want to do this in space-time. So we want to actually apply this to the actual time evolution operators themselves, rather than just looking at static configurations. Now, if you're going to be able to do this successfully, it's hard to do unless the representative variable, the variable that represents all these atoms here, is something that's spatially uniform, something that says there's basically no difference between over here and over here. So we need some variable that is spatially uniform, and then there's only going to be variation at the boundaries. And so the idea then is we do some kind of adaptive mesh refinement. That means have a big mesh inside this regime here, where your representative variable is large, has no spatial variation, and then a fine mesh at the edges where something is actually happening. So here's a kind of picture that you might have of a solid liquid boundary. So here's meant to be a crystal, here's meant to be the disordered melt. You might look at, say, the density as I go in this direction across here, and it might be high in the crystal phase and then low in the liquid phase, and then there's some transition region, some interface. So what do people do? So what traditionally people have done is they've said there's a sharp interface separating solids and liquids, so we'll impose boundary conditions on that interface. We'll write down a moving boundary problem that describes, say, how heat is transported across this interface. It's a moving boundary problem because you have to solve, say, the heat equation in a domain which is defined by the solution of the heat equation itself. So it is a nonlinear problem, somewhat akin to general relativity in that respect. And that's what people traditionally did. The phase field method is a different one. It says, since we know that this density sort of has this structure here, let's see if we can derive a nonlinear partial differential equation for this field phi, that is 1 in the solid phase, 0 in the liquid phase, or -1, and invent it in such a way that it correctly matches the boundary conditions. So for about 10 or 15 years now, people have been using exactly this kind of method, and it's not very hard to do once one sees how to do it. So here is an example of a simulation of something solidifying. Here is an example of the mesh. You can see that over here, when basically nothing is happening, the mesh is very large. Over here, when nothing is happening, the mesh is very large. Here at the interface, you can see that the mesh is very fine, as you need a lot of detail to resolve what is happening at that interface. So that is the most efficient way to spread out the computational load. Now, the problem with that method is that it gives you the wrong answer. And it gives you the wrong answer because it doesn't preserve the crystallographic orientation. I've over-coarse-grained. If I want to just say this thing has got some kind of average density, well, then I've lost the fact that the crystal axes are in the x direction and the y direction. I've lost that. And that matters when domains collide, because they have surface energy that depends upon the different orientations. So it's not a good thing to do. So the phase field crystal method is a way to get around that. So let me explain what that is. So here's going to be a bit more technical. Remember on the previous part of the talk, I showed you that free energy that described the two phases of your salad dressing, the oil-rich phase and the vinegar-rich phase. And there was a free energy function that had two minima. So the same thing is done here. Here's a free energy that is a function of density. It goes as rho squared and rho to the fourth. If this coefficient A is negative, then this function looks exactly like the one that I sketched on the previous transparency, some kind of double well potential like that. Now what you do to include the spatial structure is you say the system has an energy cost whenever there is a boundary between two different types of atoms. So you penalize departures from uniformity, and the way you can do that is say, if I have a departure from uniformity, that means that grad rho will be non-zero, and therefore I don't care which sign, whether the departure from uniformity is positive or negative, so I just square that. That's something that's analytic, so my free energy looks like grad rho squared plus this. And that's what people do. It has a ground state, which is a spatially uniform system, and that's called Landau theory. Now what we're going to try to do is we're going to say, make a minimal model. Now when we talked about the minimal model of polymers, we just said, okay, polymers are just stuff that is made out of long stringy things. Here we're going to say materials are made out of atoms, and what do atoms like to do? They like to be next to each other. They like to form a periodic ground state. So we're going to write down a free energy that penalizes not departures from uniformity, but departures from periodicity. So how do we do that? Well, if something is periodic, then it's going to satisfy some kind of harmonic oscillator type of equation, or in 3 dimensions, del squared plus q to the minus 2 of rho. That would be non-zero. This q would be the length scale of the lattice, and then if the system was periodic, this operator would be 0. If the system is not periodic, this operator acting on rho would be non-zero, and we square it to give an energy penalty, and then we have the usual double well potential. So we have a periodic ground state for this system, but it will have an energy cost if it is not periodic. Now we need to impose dynamics, and because we view this as being a density, that means that it's a conserved quantity. And so what that means is that the equation of motion for the density should be an equation that looks like this. It should be d rho by dt is del squared times df by d rho. Why something like that? Well, I have a current, which is the gradient of chemical potential. The chemical potential is df by d rho. The current is conserved, so d rho by dt is div j. If I plug that into that conservation law into this equation, then I get, if I plug the current is the gradient of chemical potential into the conservation law, then I get this equation here. And in dimensionless units, it looks like this. So what it is it's a sixth order, nonlinear partial differential equation. And this is what it looks like. So somebody asked me about Cahn-Hilliard equation. I can't remember who it was. Maybe it was you or... So anyway, so this equation is not the Cahn-Hilliard equation. The Cahn-Hilliard equation is a fourth order equation. This is a sixth order one. Okay, now you have this partial differential equation, and now you say, okay, what are the solutions to it? So you go and open Cross and Hohenberg's 1994 Reviews of Modern Physics paper, and you learn about how do you analyze the spatially extended dynamical systems, looking at their instabilities and so on and so forth. And so what you find is that depending upon this variable r, and depending upon the average concentration, there are solutions to this which are either uniform or have stripes or have a triangular lattice. And what we're going to do is we're going to focus in on this part of the phase diagram here and say this is meant to be the phase diagram of a real material. So here, for example, is argon, liquid, solid phase. This part of the phase diagram is modeled by this part of the phase diagram of this differential equation. Now, why is this a good thing to do? Well, we've preserved crystallographic information, we've captured topological defects, and we've also included elasticity in a native way. How did we do that? Well, suppose I put in, just think about the one-dimensional system, suppose I put in a periodic sine wave for the density field, psi. Okay? So then there's an equilibrium value of A, which will minimize the free energy. Let's suppose now I say the lattice is stretched, so now this value of A, this length scale, for the periodicity is now bigger than the equilibrium length scale. Then I find that there's a change in the free energy, which I can compute, and it looks like something like this. It's A minus the A squared times some coefficient. This is just Hooke's law. It just says you stretch something, and the energy cost is proportional to the square of the extension, and we can relate what that coefficient is, the spring constant, to the parameters r and psi in that partial differential equation. And we can do more than that. We can model elasticity and nonlinear elasticity and so on. So if you look at what this partial differential equation does when you solve it, starting from a random initial condition, this is what you see on the movie here. So what happens is it produces periodic patterns, which are randomly oriented. It chooses no special direction. They start to grow, and eventually they collide, and they form these grain boundaries that you can see here. These grain boundaries are arrays of topological defects, dislocations, which are strung together at those boundaries. And so this is something that is very hard to do in a normal simulation, simulating polycrystalline materials, but it's quite easy in this particular method. Now, it's not just that it produces patterns. So, for example, if I want to ask the following question, if I have a grain where everything is oriented in the xy direction, and I have another grain where everything is oriented at an angle theta to the vertical axis, as shown here, what is the energy cost of making that boundary? So in this model, I'm not going to go through how you do the calculation. You can compute that. So you can compute what the energy cost is as a function of orientation angle, and that function, if you scale it by the maximum value and the peak value, agrees very nicely with what you get from experimental data. And in fact, it satisfies various analytical results that are known in the material science literature. You can make many different kinds of patterns. So here's some patterns with fracture. Here's some patterns of growing epitaxial films. Here's some patterns showing you dislocations moving and so on. Here's an example of a movie which shows a triangular crystal undergoing a uniaxial extension and causing a fracture to then emerge, and we can see how these fractures change as a function of the angle of the uniaxial extension angle to the z-axis. We can look at multiple cracks growing from random initial conditions, and so on and so forth. All of this is very easy because all you're solving is a single nonlinear partial differential equation. One can do things like measure the critical height for dislocation nucleation in strained epitaxial films. So here's the strain, here is the height, here is some experimental data, scaled in an appropriate way. Again, these sorts of laws emerge very naturally out of this kind of minimal modeling. It's much faster than doing molecular dynamics. And the reason is because the equations of motion are on diffusive timescales. So they're many times faster. But it has a big problem. And I'm going to end the last few slides are going to be about how we solve this problem. So what is the big problem? The problem is that we're modeling at the atomic scale. You could see the atoms in those movies, and so that is still computationally expensive. I haven't done any dimension reduction at this point. All I've done is make a nice minimal model. I haven't done any dimension reduction. Now I need to do a dimension reduction. So, so what I want to do now is I want to do multi-resolution analysis on this model. But unlike the phase field model, which I showed you before, where you had a constant density in the solid phase, a constant density in the liquid phase, and some rapidly varying transition zone between them, we don't have that here because we always have periodic atomic structure. So that kind of screws things up. So the way we solve that is using this technique called renormalization group, and I want to just explain to you in simple terms what one does. If one has a periodic structure, that means it has an amplitude and phase. If it's just perfectly periodic, the amplitude will be spatially uniform, and the phase will be spatially uniform of that wave. Let's suppose you have some kind of topological defect, or you have a grain boundary, or you have a vacancy. Well, then what's going to happen, your density is going to metaphorically look something like I've sketched over here, and if I look at what the amplitude or the phase of this density wave will look like, it'll be constant up here, then it'll be rapidly varying around here, and then it'll come back to a constant value, and then it'll carry on. So the idea is, if that happens, then that's great, because we can just use an adaptive coarse-grained mesh over here, coarse-grained mesh over here, and a fine-grained mesh over here. And if we have some magical technique, which I haven't tried to describe to you, that can track in real time where these regions are and move the mesh in real time while still preserving all the bounds on the accuracy and stability of the solution, then we can use that to study these systems. Now, that would be great, but the problem is that we have an equation for the density, but what we need if we're going to do that is an equation for the amplitude and phase of the density. So how do we get that? And that's where the renormalization group comes in. So anyway, so I'm not going to go through this. So there's a very this describes a quick and dirty trick to derive the equation. So I'm not going to go through them, and you end up with three coupled equations for the amplitudes of the amplitude and phase. So you can systematically work out methods for doing that. So these are extensions of methods that are in the applied math literature, which go under the names of multiple scales analysis or boundary layer theory and so on, singular perturbation theory. The renormalization group method is better than the usual derivations for the following reasons. We don't need to assume how space and time scale with some small parameters, as is usually the case in asymptotic analysis. The usual method, you have to do a sixth-order perturbation theory. It's a complete orgy of formalism, to use Sidney Coleman's memorable turn of phrase. And the calculation I'm showing you here is just for one dimension. If you do this in 2 dimensions and 3 dimensions, you have many, many cross terms, and it's a very difficult calculation to do. So,
is 6 obvious?
What?
Is 6 obvious?
Yes, because it's a sixth-order partial differential equation.
Oh.
So you need to go to sixth order to get the multiple scales analysis.
that
to
problem,
Yes. So for this problem, so this is a dirty trick where you can basically derive the right rotationally covariant equation of motion just from the linear stability analysis. Okay. So I'm not going to go through it, but I can explain to you afterwards if you wish. So here's how well it works. So on the left-hand side is the solving the renormalization group equations. On the right-hand side is solving the brute force phase field crystal equations, and you can see that there's no real difference. Okay, now that we've got variables that vary uniformly in space, I'm going to skip over this. Then we want to see, do the amplitude and phase gradient, are they spatially uniform? So if you look at those solutions and now plot the amplitude and phase gradient, you can see that those quantities are spatially uniform over the system. And because they're spatially uniform, that means you can do some kind of adaptive mesh refinement. So I'll skip over technical details. And so when you do that correctly, and it's not a piece of cake to do this, then here's an example of that calculation. So here is the mesh. As you can see, the mesh is big inside the domains. It's big outside the domains. Inside where the domains collide, the mesh is very fine. And you can see that here in this animation. So it's possible to do this calculation. So that's great. Why is it great? It means we can do real multi-scale resolution. So here's a simple example that we just did on an old PC running Linux with polycrystalline domains. I'm not showing you the whole thing here, just the mesh. Zooming in on the mesh, these are a whole bunch of topological defects forming a grain boundary. Here we are zooming in on the grain boundary. Here we are zooming in even further. And here you can see the final stage of evolution where in fact there's two topological defects that approach each other and actually annihilate. And in this simple example, the speed up of this calculation over any other kind that you could do is about a factor of 1,000. And the higher the dimensionality of the system, the faster is the speed up. Okay, so I'm out of time.
How big system is
This one was done 700 nanometers by 700 nanometers. Okay, I'm just going to skip this. And that's the conclusion. So what I've told you is that physical predictions rely on the existence of minimal models, and they can make parameter-independent predictions of universal quantities. Very simple computational algorithms can model very simple processes, but those can generate very complicated space-time patterns. So that we already knew for a long time, but we can actually make quantitative prediction of universal quantities that are in excellent agreement with experiment. And renormalization group methods, so this is just for the physicists who are here, can be used to provide very fast quantitative multiscale modeling techniques. So, okay. So, all right, so I'll be happy to take any questions. Thank you for your attention.